Here we have a SAT math problem. Okay, let's go over the question. A circle has center A and points B and C lie on the circle. Line segments BD and CD are tangent to the circle at points B and C respectively. The measure of angle BDC is 120 degrees. The length of line segment CD is 12 inches. What is the area of the region that is both inside the quadrilateral ABCD and outside the circle in square inches? Round your answer to the nearest hundredth of a square inch. Okay, first let me draw a figure from the given information so that I'll have some clarity on what has to be done. Okay, now let me draw a figure. Here I've drawn a figure for the given information, and this figure is not drawn to scale. Some measures on the figure over here will be inappropriate. Okay, now let me mark the given information on the figure. The center of the circle is A. Okay, now let me mark A over here, and we have the points B and C on the circle. Okay, now let me take the point B over here and C over here, and the line segments BD and CD are tangent to the circle at points B and C. Okay, here when I consider the two line segments BD and CD, I find D in common. That means these two line segments drawn as tangents to the circle from the same external point, and that is D. So we can consider point D over here. And the measure of angle BDC is 120 degrees. So here we have the measure of angle BDC. This is 120 degrees. Okay, the length of the line segment CD is 12 inches. Here we have the length of the line segment, and that is a tangent 12 inches. Okay, whenever we draw two tangents to a circle from the same external point, they must be equal in length. So then the length of this line segment BD also must be 12, because both CD and BD are tangent to the circle from the same external point D. Okay, now what I'm going to do is I'm going to consider the question, that is what is the area of the region that is both inside the quadrilateral ABCD and outside the circle. So that is, we have to find the area of the region that lies inside the quadrilateral but outside the circle. So this is the area we have to find. So this area lies inside the quadrilateral ABCD over here, and also it's outside the circle. So how do you have to get the area over here that has been shaded? For that, we have to get the area of the quadrilateral ABCD over here. So once we get the area of this quadrilateral, from this area, we have to subtract the area of the sector over here. When I subtract the area of the sector from the area of the quadrilateral, I'll be getting the area of the region which lies inside the quadrilateral and outside the circle. Okay, now let's plan how to get the area of the quadrilateral. For that, let me connect the center of the circle A and the external point D. Whenever two tangents are drawn to a circle from the same external point, the two tangents along with the two radii of the circle will form a quadrilateral. And when we connect the center of the circle and the external point, that is in this case the line segment AD, it will divide the quadrilateral into two congruent triangles. The area of this triangle over here, the area of this triangle over here will be equal. Now our aim is to get the area of one of these two triangles. Once I get the area of one of the two triangles, it can be multiplied by 2 to get the area of the quadrilateral ABCD over here. And also at the point of tangency, the angle between the radius and tangent is always a right angle. That is, here we have right angle and here we have a right angle. And we know that the measure of angle BDC over here is 120 degrees. It's given in the question itself. And this angle will be bisected by this line segment AD. So this 120 degree angle measure will be divided into two equal parts. That is, a measure of angle over here is 60 degrees and the measure of angle over here is 60 degrees. Then what is the measure of angle over here? Then it has to be 30 degrees, because here we have right angle, that is 90 degrees, here we have 60 degrees, then it must be 30 degrees, so that the three interior angles of this triangle will add up to 180 degrees, and the same stuff we have over here, that is we have 30 degree angle measure over here, 30 positive 60, 90, 90 positive 90, 180. Now let me consider the right triangle ACD over here. Actually, it is a 30, 60, 90 special right triangle. In 30, 60, 90 special right triangle, the side which is opposite to the smallest interior angle 30 degrees is the shortest leg. Okay, in this triangle, CD is the shortest leg, and usually we assume X as the length of the shortest leg of a 30, 60, 90 special right triangle. Then the next longer leg is the side of the triangle which is opposite to the interior angle 60 degrees. Now to get the length of the next longer leg which is opposite to 60 degrees, we have to multiply the length of the shortest leg X by square root of 3. Then the length of this leg AC is X times square root of 3. We know that AD is the hypotenuse of this triangle because it is opposite to the right angle, and also this is the longest leg of this triangle. To get the length of this hypotenuse AD, we have to multiply the length of the shortest leg by 2, then we get 2x. Always we have to remember this stuff in 30, 60, 90 special right triangle. Already we have the length of the shortest leg CD, that is 12. Okay, instead of x, we can consider this value 12. Okay, here we can plug in 12 for x over here and here. When I do so, I am getting 12 times the square root of 3 as the length of this leg AC. And already we got 2x. When I plug in x equals to 12, 2 times 12 is 24. The length of the hypotenuse is 24. Anyways, it's not required for this problem. Okay, now in this right triangle ACD, the length of the two legs AC and CD are 12 times square root of 3 and 12 respectively. Okay, in a right triangle, apart from the hypotenuse, in the remaining two legs, we can consider one of the legs as a base and the other leg as a height. Okay, in this right triangle ACD, we can consider this leg CD as a base and this leg AC as a height. Okay, now we can get the area of this triangle ACD. Okay, now let me write the stuff over here. That is area of triangle ACD equals to, we have the formula to get area of triangle, that is a base times height divided by 2. Okay, here the base of the triangle is 12 and the height of the triangle is 12 times square root of 3. Let me plug in, divided by 2. Here 2 goes into 2 1 times and 2 goes into 12 6 times. I am getting 6 times 12 square root of 3 is 72 square root of 3. Okay, here I got the area of one of these two triangles. As I said earlier, to get the area of the quadrilateral ABCD, we have to multiply the area of one of the two triangles by 2. Okay, now let me get the area of the quadrilateral. Area of quadrilateral ABCD equals to 2 times the area of one of the two triangles, that is 72 times square root of 3. Then we get 144 times square root of 3. Okay, here I got the area of this quadrilateral ABCD. Now my aim is to get the area of the sector over here, and there is a formula to get area of a sector. Okay, let me write the stuff over here. Area of sector equals to, actually the sector is a part of the circle, theta divided by 360 degrees times the area of the square, that is pi square. Okay, here this theta is the central angle of the sector. Okay, this is the central angle of the sector. The measure of the central angle of the sector is 30 positive 30, that is 60 degrees. Okay, now let me plug in 60 degrees for theta over here, divided by 360 degrees times pi. This R represents the radius of the circle. Actually, the line segment AC over here represents the radius of the circle. Its length is 12 times square root of 3. That is, the radius of the circle is 12 times square root of 3. Okay, now let me plug in 12 times square root of 3, the whole square. Okay, here 60 goes into 60 1 times and 60 goes into 366 times. I am getting 1 over 6 times pi times. Okay, here two values are multiplied and there is a common exponent 2. Now we can take this exponent 2 for these two values separately and multiply the results. Then I'm getting 12 square times square root of 3, the whole square. Okay, 1 over 6 times pi times, the value of 12 square is 144. And here this square and square root will cancel out. I am getting 3. Okay, 6 goes into 6 1 times and 6 goes into 24 times in 144. Okay, here 1 times pi is pi. Pi times 24 is 24 pi. 24 pi times is 72 pi. Here we got the area of this sector, that is 72 pi. As we planned earlier, to get the area of the region which lies inside the quadrilateral and outside the circle, we have to subtract the area of this sector, 72 pi, from the area of the quadrilateral ABCD, that is 144 square root of 3. Okay, now let me write the stuff over here. That is the required area equals to the area of the quadrilateral 144 times square root of 3, negative area of the sector, that is 72 pi. Okay, we'll be getting this area in square inches because we have one of the measurements, that is the length of line segment CD is 12 inches. So all the areas that we get over here, here and here will be in square inches. Okay, now we have to evaluate the value of this expression and round our answer to the nearest hundredth of a square inch. Okay, now we can go to Desmos graphing calculator to evaluate the value of this expression. Here we have Desmos graphing calculator. Okay, now let me give the expression as input. That is 144 times square root of 3 negative 72 pi. Okay, here I got the value of the expression, that is 23.2206. It keeps going. According to the instruction, we have to round this value to the nearest hundredth. Then I'm getting 23.22. Therefore, the required area is 23.22 square inches.